ASTM C138 is the standard test method for density, unit weight, yield, and air content, gravimetric, of concrete. This test method covers the determination of the density of freshly mixed concrete and gives formulas for calculating the yield and final cement content. Yield is defined as the volume of concrete produced from a mixture of known quantities of the component materials. This presentation does not suggest to address the safety concerns associated with this procedure. It is the responsibility of the viewer of this presentation to follow all safety procedures, rules, and standards established by private companies, government agencies, and construction site supervisors. This presentation uses both inch-pound units as well as SI units. These units shall be regarded as separate. In other words, the value of one unit shall not be considered the exact equivalent of the other. Therefore, the units shall not be considered interchangeable. Any conflating of the two systems may result in non-compliance of this standard. To perform this test, we'll need a balance or scale accurate to 0.1 pounds, or 45 grams, or within 0.3% of the test load, whichever is greater, at any point within the range of use. The range of use shall be considered to extend from the mass of the measure empty to the mass of the measure plus its contents at 160 pounds per cubic foot, or 2,600 kilograms per cubic meter. The rod shall be a round, smooth, straight steel rod with a 5/8 inch or 16 millimeter diameter. The length of the tamping rod shall be at least 4 inches or 100 millimeters greater than the depth of the measure in which the rodding is being performed, but not greater than 24 inches or 600 millimeters in overall length. The rod shall have the tamping end, or both ends, rounded to a hemispherical tip of the same diameter as the rod. The vibrator frequency shall be at least 9,000 vibrations per minute, or 150 hertz, while the vibrator is operating in the concrete. The outside diameter or the side dimension of the vibrating element shall be at least 0.75 inches, or 19 millimeters, and not greater than 1.5 inches, or 38 millimeters. The combined length of the vibrator shaft and vibrating element shall exceed the depth of the section being vibrated by at least 3 inches, or 75 millimeters. The vibrator frequency shall be checked with a vibrating reed tachometer at an interval not to exceed 2 years. If the vibrator manufacturer recommends a shorter verification interval, a verification procedure, or other verification device, the manufacturer's recommendation shall be followed. We'll also need a measure, a cylindrical container made of steel or other suitable metal. The minimum capacity of the measure shall conform to the requirements of the table seen here, which is based on the maximum aggregate size in the concrete. All measures, except for measuring bowls of air meters, which are also used for this procedure, shall conform to the requirements of ASTM C138. We're going to need a strike-off plate, a flat rectangular metal plate at least 1/4 inch thick, or 6 millimeters, or a glass or acrylic plate at least 1/2 inch thick, or 12 millimeters, with a length and width at least 2 inches, or 50 millimeters greater than the diameter of the measure with which it is to be used. The edges of the plate shall be straight and smooth within a tolerance of 1/16 of an inch, or 2 millimeters. A mallet is also necessary. The mallet, with a rubber or rawhide head, shall have a mass of 1.25 pounds, plus or minus 1/2 pound, or 600 grams, plus or minus 200 grams. For use with measures of 0.5 cubic feet, or 14 liters or smaller, and a mallet having a mass of 2.25 pounds, plus or minus 1/2 pound, or 1,000 grams, plus or minus 200 grams, for use with measures larger than 0.5 cubic feet, or 14 liters. And of course, we'll need a scoop. When measuring bowls of air meters are used, they shall conform to the requirements of ASTM C138 and shall be calibrated for volume as described in ASTM C139. The top rim of the air meter bowls shall be smooth and plain within 0.01 inches, or 0.3 millimeters. Base the selection of the method of consolidation on the slump, unless the method is stated in the specifications under which the work is being performed. If the slump of the concrete is greater than 3 inches, or 75 millimeters, the concrete must be rodded. When rodding, the measure must be filled in 3 equal layers. Rod each layer with 25 strokes of the tamping rod when nominal 0.5 cubic feet, or 14 liters, or smaller measures are used. 50 strokes when nominal 1.0 cubic feet, or 28-liter measures are used. And 1 stroke per 3 square inches, or 20 square centimeters of the surface for larger measures. Rod each layer uniformly over the cross-section with the rounded end of the rod, using the required number of strokes. If the slump of the concrete is less than 1 inch, or 25 millimeters, the concrete sample must be vibrated. When vibration is the consolidation method, the measure must be filled into equal layers. The vibrator must be inserted at least 3 locations across the surface area of the concrete. Be sure that all the concrete, for each layer, has been placed in the measure before the vibration begins. Under normal circumstances, one can assume that sufficient vibration has been achieved when the surface of the concrete is relatively smooth. Be sure not to over-vibrate the concrete, as this may cause segregation and loss of entrained air. If the slump of the concrete is between 1 inches, or 25 millimeters, and 3 inches, or 75 millimeters, either consolidation method is acceptable. Now that we have gone through the basics of ASTM C138, let's go through a detailed performance review of the procedure and perform our required calculations. Here, we're going to be using an air meter bowl and the rodding method. Obtain a sample in accordance with ASTM C172, standard practice for sampling freshly mixed concrete. Dampen the interior of the measure and remove any standing water from the bottom of the measure. Determine the mass of the measure being used to the nearest 0.1 pounds, or 0.01 kilograms. For this example, the weight of the measure is 8.8 pounds, or 3.99 kilograms. Place the measure on a flat, level, firm surface and add the first layer of concrete. Move the scoop around the perimeter of the measure opening to ensure an even distribution of the concrete with minimal segregation. Since our measure is less than 0.5 cubic feet, or 14 liters, we will rod each layer 25 times. As always, we'll use the rounded end of the tamping rod. We'll rod the first layer throughout its depth. We now want to tap the sides of the measure 10 to 15 times with a mallet, using such force as to close any voids left by the tamping rod and to release any large air bubbles that may have been trapped. We can now add the second layer of concrete, again moving the scoop around the perimeter of the measure to ensure even distribution and minimize segregation. The second layer should fill the measure to approximately 2/3 its volume. We now want to rod the second layer 25 times. The second layer is rodded throughout its depth, penetrating the previous layer by approximately 1 inch, or 25 millimeters. Once again, tap the sides of the measure 10 to 15 times with the mallet, using such force as to close any voids left by the tamping rod and to release any large air bubbles that may have been trapped. We can now add the third and final layer of concrete, taking care not to overfill the measure. Rod this layer 25 times, penetrating the previous layer by about 1 inch, or 25 millimeters. Tap the sides of the measure 10 to 15 times with the mallet. After tapping the third layer, but before striking off, a small quantity of representative concrete can be added or removed to compensate for slight deficiencies or excesses. 1/8 of an inch, or 3 millimeters above the rim of the measure, is considered optimum. We can now strike off the measure. Press the plate on the top surface of the concrete, covering approximately 2/3 of the measure. Then, in a sawing motion, withdraw the plate to finish only the area that's been covered. Now, put the plate back on top of the measure, covering only the original 2/3 of the surface. Then, with vertical pressure, in a sawing motion, advance the plate off the measure. Incline the plate and perform final strokes with the edge of the plate to produce a smooth surface. After strike-off, clean all excess concrete from the exterior of the measure and determine the mass of the concrete in measure to the nearest 0.1 pounds, or 0.01 kilograms. For our example, assume the weight to be 43.4 pounds, or 19.69 kilograms. Now, as we prepare to do the calculations, the volume of the measure used must be reported to the nearest 0.001 cubic foot, or 0.01 liters, and the density, or unit weight, is reported to the nearest 0.1 pounds per cubic foot, or kilograms per cubic meter. Because the yield calculations reported vary between inch-pound units and SI units, we will do the calculations separately. First up, inch-pound units. To calculate the density unit weight, we use the equation D equals m subscript c, the mass of the measure filled with concrete, minus m subscript m, the mass of the measure empty, divided by v subscript m, the volume of the measure. So, what is our density unit weight of this concrete? The measure filled with concrete weighs 43.4 pounds. If we subtract the weight of the measure empty, which was 8.8 pounds, the concrete itself weighs 34.6 pounds. We can now divide the weight of the concrete by the volume of the measure, or 34.6 pounds divided by 0.250 cubic feet. Gives us a unit weight of 138.4 pounds per cubic foot. Let's assume the unit weight was calculated in the field, and now we have to calculate the yield and final cement content. The concrete was designed for 1,800 pounds of stone, 1,096 pounds of sand, 600 pounds of cement, and 300 pounds of water. Furthermore, we have ordered 7 yards of concrete. So, the total mass of all materials batched in the truck is 26,572 pounds. We are at the job site, and we are handed a ticket that tells us the weight of all materials batched is 26,572 pounds. We have ordered 7 cubic yards of concrete. The unit weight is 138.4 pounds per cubic foot. We are now going to calculate the yield per batch in cubic feet, the yield per batch in cubic yards, and the yield of cubic feet per cubic yard. After which, we will make the final cement content calculation. To calculate the yield per batch in cubic feet, the calculation is m divided by d, where m is the weight of all materials batched, and d is the density, or unit weight, of the concrete. In this case, that is 26,572 pounds divided by 138.4 pounds per cubic foot, equals 192 cubic feet of concrete. This is the yield in cubic feet. To calculate our yield in cubic yards, the calculation is m divided by d times 27. M, again, is the weight of all materials batched. D is the density, or unit weight, and 27 is the amount of cubic feet in a cubic yard. So here, we ordered 7 cubic yards of concrete. But how much did we get? 26,572 pounds divided by 138.4 times 27, or 3,737, equals 7.1 cubic yards. So here, we are pretty much on target, maybe slightly over-yielding. Now, let's calculate the yield of cubic feet per cubic yard. Here, the calculation is y subscript f divided by y subscript d, where y subscript f is the yield in cubic feet, and y subscript d is the yield in cubic yards for which the batch was designed. So, the calculation is 192 cubic feet divided by 7 cubic yards, gives us a yield of cubic feet per cubic yard of 27.4. That is 27.4 cubic feet per cubic yard. So we are definitely over-yielding. To calculate relative yield, the equation is y divided by y subscript d, where y is the yield, and y subscript d is the yield for which the batch was designed. Relative yield can be calculated for cubic feet, cubic yards, or cubic feet per cubic yard. Here, we see the yield for cubic feet is 192, the actual yield, divided by 189, the amount of cubic feet for which the batch was designed, gives a relative yield of 1.01. Next, 7.1 cubic yards divided by 7 cubic yards gives us a relative yield also of 1.01. And lastly, 27.4 cubic feet per cubic yard divided by 27 cubic feet also gives us a relative yield of 1.01. A value for relative yield greater than 1.00 indicates an excess of concrete being produced, whereas a value of less than 1.00 indicates the batch to be short of its design volume. In the inch-pound system, a ratio of yield in cubic feet per cubic yard of designed concrete mixture is frequently used. With the yield calculations complete, we can calculate our actual cement content. The equation for cement content is C equals C subscript B divided by Y, where C is the actual cement content, C subscript B is the total cement batched, and Y is the yield in cubic yards. So here, the cement batched, or CB, is 4,200 pounds, 600 pounds of cement times the 7 yards of concrete for which we designed. The yield has been established to be 7.1 cubic yards. Therefore, 4,200 pounds divided by 7.1 cubic yards equals 592 pounds per cubic yard. This is sometimes a tough concept for some. But think of it this way. If the amount of concrete is increasing, or over-yielding, with 4,200 pounds of cement batched, then the cement per cubic yard has to decrease. And finally, let's calculate our air content, gravimetric. Here, the equation is A equals T minus D divided by T times 100, where A is the air content of the concrete. T is the theoretical density of the concrete computed on an air-free basis in pounds per cubic foot, and D is the density, or unit weight, of the concrete. So here, our theoretical unit weight is 140.6 pounds per cubic foot. We'll discuss this number in a moment. For now, let's complete the equation. Our density is 138.4 pounds per cubic foot. Therefore, our equation is 140.6 pounds per cubic foot minus 138.4 pounds per cubic foot divided by 140.6 pounds per cubic foot equals 1.6% air. Now, let's explain that theoretical unit weight number. The theoretical density is usually determined in the laboratory. The value is believed to remain constant for all batches made using identical concrete constituents and proportions. So here, we have 1,800 pounds of stone, 1,096 pounds of sand, 600 pounds of cement, and 300 pounds of water. The weight of our total materials batched is 3,796 pounds, divided by 27 cubic feet, gives us a theoretical unit weight of 140.6 pounds per cubic foot. We'll now do our calculations in SI units. To calculate the density, unit weight, we must use the equation D equals M subscript C, the mass of the measure filled with concrete, minus M subscript M, the mass of the measure empty, divided by V subscript M, the volume of the measure. So what is our density unit weight of this concrete? The measure filled with concrete weighs 19.69 kilograms. If we subtract the weight of the measure empty, which was 3.99 kilograms, the concrete itself weighs 15.70 kilograms. We can now divide the weight of the concrete by the volume of the measure. You may recall the measure reported in liters. The measure was 7.08 liters. If we convert 7.08 liters to cubic meters, the volume of our measure is 0.0071 cubic meters. Therefore, the density of our concrete is 15.7 kilograms divided by 0.0071 cubic meters, or in this case, 2,211 kilograms per cubic meter. This example states that you are a contractor at a job site. You have reached out to a concrete producer, and you have agreed with them on the design proportions of the concrete mix. The batch information provided indicates that in 1 cubic meter of freshly mixed concrete, there are 1,028 kilograms of coarse aggregate, 715 kilograms of sand, 335 kilograms of cement, and 156 kilograms of water. After agreeing with the concrete supplier on the concrete design specifications, you have placed an order of 5 cubic meters of concrete. Provided all the given information, You are now requested to calculate the concrete yield and the relative yield. The concrete yield is denoted as Y, and it is the volume of concrete produced per batch in cubic meters. It is calculated based on the equation shown. Y is equal to m divided by d. M represents the total mass of the materials batched in kilograms, and d represents the density or unit weight of concrete in kilograms per cubic meter. So we are at the job site, and we are handed a ticket that tells us the weight of all materials batched is 11,170 kilograms. We have ordered 5 cubic meters of concrete. The unit weight is 2,211 kilograms per cubic meter. We are now going to calculate the yield per batch in cubic meters, the relative yield, and the actual cement content in kilograms per cubic meter. From the previous slide, we have obtained that the total mass of the materials present in the received batch is 11,170 kilograms. D, which is the unit weight of concrete, was calculated to be 2,211 kilograms per cubic meter. The concrete yield is calculated by dividing the total mass of the batched materials by the given unit weight of concrete. That would be 11,170 kilograms divided by 2,211 kilograms per cubic meter, giving us a yield that is equal to 5.1 cubic meters. After calculating the yield, we can now calculate the relative yield. The relative yield is the ration of the actual volume of concrete obtained to the concrete volume as designed for the batch. It is denoted as R subscript Y, and it is equal to Y divided by Y subscript D. Y represents the volume of concrete produced per batch in cubic meters, and we have calculated that in the previous slide. And Y subscript D is the volume of concrete which the batch was designed to produce in cubic meters. In this example, Y subscript D is given as 5 cubic meters. Moving on, the relative yield is calculated as follows. Y, which is equal to 5.1 cubic meters, divided by Y subscript D, which is equal to 5, gives us a relative yield of 1.02. First, it is important to remember that a relative yield that is greater than 1.00 indicates that an excess of concrete is being produced, whereas a value less than 1.00 indicates the batch is short of its design volume. In this case, you can see that R subscript Y is slightly greater than 1. Therefore, for this batch of concrete, there is a slight overyield. Let's go ahead and calculate our final cement content in kilograms per cubic meter. With the yield calculations complete, we can calculate our actual cement content. The equation for cement content is C equals C subscript B divided by Y, where C is the cement content, C subscript B is the total cement batched, and Y is the yield in cubic meters. So here, the cement batched, or CB, is 1,675 kilograms. 355 kilograms of cement multiplied by the 5 cubic meters of concrete for which we designed. The yield has been established to be 5.1 cubic meters. Therefore, 1,675 kilograms divided by 5.1 cubic meters equals 328 kilograms per cubic meter. This is sometimes a tough concept for some. But think of it this way. If the amount of concrete is increasing, or over-yielding, with 1,675 kilograms of cement batched, then the cement per cubic meter has to decrease. And finally, let's calculate our air content, gravimetric. Here, the equation is A equals T minus D divided by T times 100, where A is the air content of the concrete. T is the theoretical density of the concrete computed on an air-free basis in kilograms per cubic meter, and D is the density or unit weight of the concrete. So here, our theoretical unit weight is 2,234 kilograms per cubic meter. Our density is 2,211 kilograms per cubic meter. Therefore, our equation is 2,234 kilograms per cubic meter minus 2,211 kilograms per cubic meter, divided by 2,234 kilograms per cubic meter gives us an air content, gravimetric, of 1.0%. The theoretical density is usually determined in the laboratory. The value is believed to remain constant for all batches made using identical concrete constituents and proportions. So here we have 1,028 kilograms of stone, 715 kilograms of sand, 335 kilograms of cement, and 156 kilograms of water. The weight of our total materials batched is 2,234 kilograms. This is our theoretical unit weight per cubic meter. And this concludes ASTM C138, Standard Test Method for Density, or Unit Weight, Yield, and Air Content, Gravimetric of Concrete.